Well, this week I'm going to carry on playing with my high voltage ESD generator. So I think I really need to say, for anybody who's thinking of having a go at building one of these ESD guns, or just in general messing around with these high voltage generators, my advice is probably better not to do it, because you could actually get a really nasty electric shock, or worse still, you could kill yourself. So in my opinion, these small, relatively low power but high voltage flyback transformers, they are relatively safe, although it's not to say that they can't deliver a really nasty and painful electric shock. But when you start to add these high voltage smoothing capacitors, everything becomes a lot more unsafe, because potentially you can store quite a lot of energy there at high voltage, and if you actually discharge that across your body, you stand a really good chance of stopping your heart, because what you've actually just built is a defibrillator. So I really have to repeat the warning: don't mess around with high voltages, particularly don't mess around with high voltages and large capacitor banks. Just don't do it. The only thing that qualifies me to do it is I'm an idiot. So we've got the little high voltage flyback transformer here, which actually creates the HV, and then we've got this Vardy voltage doubler. So that takes us from about 5,000 volts to about, well, I think it took us to about 10,000 volts. And then we're rectifying that, and then we've got a couple of stages of smoothing. So all this is just about creating a source of high voltage, and then this is what I would call the human body model. So we've got this 50 meg ohm resistance, we've got a discharge set of resistors here which are 350 ohms, but importantly we've got this capacitor here which is a high voltage doorknob capacitor. And the value of this capacitor was 100 picofarad. So the whole point of this this part of the circuit here, these resistors, this capacitor, and the resistors here, this is actually to emulate the actual human body and the actual electrical charge stored into it. Where this part of the circuit here is actually the equivalent of walking along your nylon carpet. So this is actually a high voltage generator, and this is just representing the human body model. So our little flyback transformer here, along with our Vardy voltage doubler, it was actually quite capable of generating 10,000 volts or more. But the problem wasn't the high voltage output. The problem that I really had is I couldn't turn the voltage down low enough, because I want to be able to actually have the output voltage from this device variable, and I want to be able to vary it from about 1,000 to, well, hopefully in a perfect world, maybe up to about 15,000 volts. And the problem with this little oscillator and its feedback winding to this transistor here is that when you actually reduce the supply voltage, the actual secondary voltage does fall, but unfortunately this actually stops oscillating when the output voltage is about 3,000 volts, and it's because there isn't enough feedback from the feedback winding to actually operate this transistor and make it oscillate properly. So there's a bit of a limitation here. Now, one of the other problems that I had with this transformer is, even though I'd actually covered it in conformal coating and tried to insulate it, whenever I ran it, it actually was giving off a really strong stink of ozone, and it was actually making, that kind of high voltage hissing noise. So if any of you have worked with like high voltage transformers and old CRTs and televisions in the past, you'll all be very familiar with that sound of when you've got high voltage leaking to ground somewhere. So I think this transformer was actually starting to break down, and I'm not really sure how much longer it would have lasted. So I think that's another reason why we need to try to change our circuit design and try some alternative components. Well, I showed you last time that I'd bought this other transformer. I've got a couple of these, and I'm hoping that this one is going to perform a little bit better in that it's fully encapsulated, it's potted in epoxy, so I'm hoping that it isn't going to break down in the same way that the other transformer did. Now, unlike the other transformer that I was playing with, it actually doesn't have a feedback winding, so it's not the type of transformer that will self-oscillate. So what we've actually got to do here, we've actually got to feed this with a square wave, and we're going to have to build a little driver circuit which is capable of producing current pulses, which we're going to feed into the primary, and this transformer is going to step it up, and that's how we're going to get the high voltage out of the secondary here. So let's go ahead and have a look at this this pulse driver circuit we're going to build. Now, I've got to admit right up front, there's nothing particularly exciting about this. It's based on a 555 timer, which I know everybody's familiar with, and we don't really need to spend a lot of time talking about that. This is actually going to produce an output square wave. The output square wave is going to drive the gate of this MOSFET here, We've got a flyback protection diode here. Got another diode here which is slightly unusual. I think the purpose of this additional diode, I think it's to actually allow this this transformer to oscillate slightly. I think you would probably call it a freewheeling diode. So that's a flyback protection diode, but I think you would call it a freewheeling diode. So it's allowing this transformer to actually oscillate. So the way that this circuit works is one side of the winding we connect a positive supply, and then the opposite side of the winding we're going to pull that to ground. And I'm guessing, I haven't worked out what the timing value is, but I'm kind of guessing that we'll probably want to feed this with around 10 kilohertz or something like that. Slightly unusually, you've got a couple of diodes here which I haven't seen used with 5.5 timers before. I think that the purpose of this is to actually modify the duty cycle from a square wave to maybe a pulsed output. So when we've gone ahead and built this part of the circuit, before we actually hook it up to the MOSFET and the coil, I think we'll just put a scope on that and have a look at it. Now I'm sure that some of you have already spotted some problems with this circuit. I mean, I did say that I needed to get away from a transformer that was self-oscillating, so that's what the 555 timer did. But unfortunately we still don't really have a way of varying the output voltage here. Now there's a couple of ways we could try to do that. Now one way we could actually try to do that is actually by changing the drive to our MOSFET here, so that we actually maybe don't pull the transformer quite to ground. So what we could do is we could actually put a variable resistance in there, and that would actually change the drive current going into our MOSFET. But there would be a problem. I might try that anyway, but it's very unlikely to work. The thing about MOSFETs in this type of application, you don't want to operate them in what they call the linear region. You actually want to drive them into saturation. So you either want this transistor turned fully on or turned fully off. You don't want to turn it halfway on, because if you turn it halfway on, it's going to be kind of resistive, and if it's resistive, you're going to have current and a resistance. It's going to start dissipating power, and this transistor, this MOSFET, will probably get very hot. So it's quite difficult to control the output by effectively changing the gate voltage to the MOSFET. So I'm planning on having a go at doing something slightly different. So to adjust the supply voltage to our coil, I'm going to be using this LM317, which is a pretty famous voltage regulator used in a lot of power supplies. I say I'm going to use one of them. I haven't actually checked to see if I've got one in the junk box, so fingers crossed, eh? And we're going to feed the output from that directly into the coil. Now we've got a couple of more components here. We've got a feedback resistor coming from the output, and we've also got a variable resistance here. So this will be a control on our ESD gun, and in theory we'll be able to turn this variable resistor up and down, which is going to change the supply voltage to our coil, and it's going to allow us to set the output voltage for anything we want, from maybe about 1000 volts hopefully to about 15 kV. So that's certainly the plan anyway. We're going to need probably quite a lot of smoothing on here, and we may actually use some capacitive resistance smoothing, because we might find that it's all very noisy, this coil driving circuitry, and it's quite likely it's going to actually cause problems with our voltage feedback and stuff like that. So I don't exactly know. I haven't really shown any of the component values on here because, you know, again, all part of the experimentation. I'm not exactly sure what this circuit will end up looking like. All part of the fun. Now, when it comes to building Veroboard circuits, I don't actually claim to be very good at it. I'm actually pretty awful. So I'm going to start off with this huge piece of Veroboard, but I'm not actually trying to optimise this design at the moment. It's just an experimentation. And, well, God, at one time Veroboard was really expensive, but of course you can actually buy Veroboard now for practically nothing from China. So at one point in my life I would have tried to have fitted this circuit into one little tiny corner so that we had all this Veroboard spare, but now it costs so little, I'm not going to bother to do that. But the other reason that I'm using such a big piece of Veroboard is I'm going to be doing quite a lot of experimentation to find out what works and what doesn't, and I'm planning on building this circuit and building it up in various blocks and modules, and I'm going to keep those blocks and modules separate. And when I've actually got the thing working to my satisfaction, I'll maybe either, you know, do a new Veroboard circuit, or I may even go ahead and you know, get a cheap printed circuit board made from China. Or maybe I was actually thinking it might be quite a laugh to you know, take a trip down memory lane and etch my own circuit board again. I mean, growing up as a kid we actually used to do that kind of thing all the time, didn't we? All etched our own circuits. But now, again, you can probably get a circuit delivered from China for like circuit board for like £10 or something. So it's not really economic to do yourself. You can't even buy the chemicals, the ferric chloride, and then you've got to dispose of them, and it's very messy. But on the other hand, you know, there's a lot to be said for the craft and the fun of just doing these things because you can. So we may have a go at rolling our own circuit board. I really haven't decided. Got a couple of heat sinks that we might use there. Again, maybe not ideal. I'm not exactly sure how big a heatsink we will need. This is the MOSFET transistor that I found, which is an IRF 520, which I think it's a lower specification than the one that they use in their circuit. But at the end of the day, the one that they use in the circuit that I showed you before, that's for a car ignition coil, so it's probably far more overrated than what we need for our little coil, which we're going to find. Here's our little coil here. Now I don't think I'll actually mount the little coil. Shall we mount the coil on the Vera board? I was going to say I think it might cause problems flashing over with the adjacent tracks. I don't think really that would be a good idea. Maybe we'll mount it something like that rather than having the high voltage pins coming out of it. That's a decision we'll make later. Well, as you can see, I brought you back about that point in the proceedings where I just burn out a 555 timer, which is always interesting, isn't it? Now, I'm afraid when it comes to building things on Vera board, I'll be the first one to admit I'm not really very good at it. This circuit that I've built, it's very messy, and I'm sure that it could have been laid out 100 times better than I've done it, because I am just not very good with Vera board. I've never had a lot of luck with Vera board, to be quite honest, because a lot of my electronics is fairly high speed digital electronics and micros and stuff like that. And I've always had a lot of trouble with things like, you know, the capacitance on the Vera board. And again, the other thing that I always used to play with is radios. It's very hard to build radios on Vera board because there's that much capacitance between the tracks. It actually affects everything. So I would have thought this is fairly low frequency. It should be okay. But of course, all these lovely long tracks, these antennas, they're going to be absolutely perfect for picking up the electrostatic discharge. So I don't know whether or not this will work or not. We'll give it a go. Well, as you can see, I've gone ahead and I've connected up the power to our little circuit here, and you can see we've got an LED glowing, which on this occasion isn't just for the old wankery value, because I do actually think it's useful to actually show when this circuit is energised. So we put a power indicator on, because that might just save me from getting an electric shock. So you can see on the oscilloscope here we've got an output from our 555 timer, and it's actually it's a pulse output, and we're going to connect that pulse output to the gate of our MOSFET, and that's what we're going to use to actually drive our flyback transformer. Now we've got a variable resistor on this little driver board, so what we can do is we can actually tweak, we can change the mark to space ratio of our square wave, because we probably don't want an even duty cycle. We probably want to produce it, we want to fire our coil with pulses like this, because what we're actually going to do is we're going to put a pulse of current into our transformer, and then the transformer will ring. When we take the power off it, it will ring, it will self-oscillate, and it's that ringing, it's that flyback which is going to generate our high voltage. Now the only problem that I do see with our circuit is the frequency here. It's only 70 Hertz. Now I actually cribbed this circuit from something that was used to drive a car ignition coil, so I'm guessing that they're probably running at much lower frequency. So we're going to have to tweak some of the timing components, because I would have thought that we've, you know, to actually make this transformer work properly, I would have thought we probably want to be around the 10 kilohertz range. So we've really got to change our component values quite a lot. But for now, I'm actually just going to proceed as it is. I'm going to actually build our MOSFET driver stage, because it'll still work even with this pulse. It just won't produce an optimal output. So let's go ahead and do that. Well, as you can see, I've gone ahead and I've wired up our MOSFET driver here, and I'm about ready to actually connect our flyback transformer. But before I do that, I just need to determine which is the primary and the secondary, because nothing's actually marked on it. I can't see any indication. And of course that should be really quite easy to do, because the actual secondary winding is going to have many thousands of very fine turns of wire. So that's going to be the high resistance side, and then the actual primary side of the winding is going to be low resistance. So let's just see what that is. Okay, so that's 0.5 ohms. Let's just check the other side. 2 kilo. Okay. So fairly sure that the 0.5 ohm side, that's going to be our primary. So I think I better just make a mark on that. And I may as well just go and mark my secondary, because if I can get it wrong I will do. So there's secondary. And the other thing I mustn't forget to do is actually put our little spark gap on here, because when I looked at the eBay listing again, it did say it was very important that you don't run this transformer without a spark gap, without a load on the secondary, because what will happen is the insulation inside there, it will flash over and damage the transformer. So we just need to go ahead and put a little spark gap in there. Well, as you can see, I've gone ahead and I've connected my 555 timer and the output driver. I've connected this to our flyback transformer and I've got it powered up at the moment, and you can see that I've also connected this voltage doubler and also some smoothing. Now the main reason that I've connected the smoothing and the doubler is it's actually much easier just for me to get a reading on our voltmeter here. So the first thing I can actually say is this output transistor here, it's stone cold. It's, you know, it's not warmed up even slightly, and yet we are getting 10,000 volts out of this. But I think we have got a problem with the driver board. It's running at much too low a frequency. At the moment it's only running at like 70 Hertz. Well, really it wants to be running at 10,000 or 15,000, so that's not great. But having said that, I am still reasonably hopeful with this, that even though it's not running optimally at the moment, you can see that we're actually still getting some sparks and some power. So I actually think our little flyback transformer here, this one that's been fully potted in epoxy, I think this is an awful lot better than the one that I was using previously, so I've got high hopes for this. Now I think I've got to go ahead now and I've got to rejig this driver circuit, because it's just not right, and maybe got to try and just retune it to maybe get an output of, as I say, around 15 kilohertz, something like that. So I'm going to take this away now and play with it a little bit more and see if we can do any better, because I think we can. Well, as you can see, I've gone away and I've just modified some of the timing components on my circuit board, and I've actually got it running as fast as I can get it to run with this 5.5 timer, and it's running at just under 2 kilohertz at the moment. And I've had it running like this for about 20 minutes as kind of a little bit of a burning test to make sure nothing gets hot. Well, at the moment my output transistor, it is actually getting warm, but I can actually still put my fingers on it. But the other thing that I've done is I've actually just kind of simulated having our adjustable 317 regulator. I've actually split the power supplies at the moment, so I'm actually feeding the oscillator with this 9-volt battery, and I'm actually feeding the main supply to our flyback transformer just from my variable power supply. So hopefully what I can achieve now is what I wanted to do. I can actually turn this down. That's annoying, isn't it? So I'm going to turn this down and I'm going to choose to set this at, say, 10,000 volts. So there you go, I can now set 10,000. Let's have a go at setting 5,000. So there's just over 5,000 volts. And let's see if I can set to 1,000 volts. And let's see if we can go to the low end. Let's see if I can actually set 500 volts on it. So there's just under 500 volts. And now let me turn it right back up. Let's see if we can set it to 15,000 volts output. So we can actually go even higher in voltage, but unfortunately it appears that my little Varney voltage doubler, it's breaking down here. Let's give it a bit more beams. Let's see it break down again, because that's exciting. And the ESD there has actually taken out my meter, but I'm fairly sure it'll come back. And let's set it to something a bit more reasonable. And as you can see from the display on our power supply, for our 7.7 volts in, we're actually getting an out of about 13,000 volts at the moment. And we've actually got far more power than we actually need here. Well, I'm afraid, as per usual, I haven't given a great explanation of how this works, but I would say for anybody who's thinking of building one of these, there's a couple of key points that I think are semi-important. It's quite useful to have a voltage doubler stage as I'm using, or maybe even a tripler stage. And the reason that's so important or so useful is if you actually do the voltage doubling, if you do the voltage magnification outside of the flyback transformer, it means that the actual windings in the flyback transformer are much less stressed, and it's much less likely to flash over and be damaged. Now the reason that I found that out is I did actually try removing the doubler stage, because this transformer has got absolutely bags of voltage magnification. It can really create a high voltage, and with the MOSFET driver it was easily capable of straight generating 15,000 volts without the doubler. In fact, the manufacturers say 20,000, and I actually believe them. I'm sure this transformer can output 20,000 volts. But what I found is when I actually removed the voltage doubler stage and I was just running the transformer with a straight 15,000 volt output, I could hear it complaining. I could hear the windings starting to whine and howl, and I took that as not being a good sign. Now I know that things like television line output transformers, they run screaming like that all day, but I didn't think it was a good idea to run the transformer so hard. So I think it's probably better to have a relatively low step-up voltage, maybe to 5,000 or 6,000 volts, and then if you want to go higher, to actually use voltage multipliers, whether you use doublers or triplers or something like that. And I'm guessing that's why they do it in a television. They don't just go from from 100 volts up to 30 kV. They actually go so far, maybe up to 10,000 volts, and then they use doubler and tripler stages. Well, for you it may only be a matter of seconds, but for me it's a few weeks later, because unfortunately I have been somewhat busy at work recently and I just haven't had much time to play with our ESD gun. Now, while I may have been at work during the day, I've actually used my night time to draw up the body of the ESD gun using Fusion 360. And as you can see, I'm actually using my 3D printer here to print out the body of the ESD gun. And unfortunately it's relatively large, so what I've had to do is I've had to print it out in a number of separate parts, and I'll be bolting and screwing those parts together to build up the complete ESD gun. Anyway, for no particular reason apart from I want to, I've actually got the tip of our ESD gun. This is what's going to inject the high voltage into our device under test. And what I've actually got here, I've got a string of resistors, and those resistors actually build up a value of 350 ohms. And what these resistors are designed to do, they're designed to actually simulate the resistance, probably in my finger. So when I would be walking along charging my body up with electrostatic charge, I want to be able to discharge the ESD gun in a similar way that my body would do it. So I'm guessing that this 350 ohms, it's representing the human body, the resistance of it. And I've actually got a piece of brass that I've machined here, and that's going to slide into this tube, because what we need to be able to do is, depending on what type of test you do, there's different contact tips that you have to put in contact with the device under test when you're hitting it with the electrostatic discharge. So I've machined out a piece of brass and I've soldered the resistors onto one end, but the other end, where I've just got this bolt to hold it at the moment, that's where we're going to have to screw on different types of contact tip. And I think what I need to do is really get as much of this epoxy into our tube here as possible. I do like playing with epoxy glue, it's somehow very satisfying. And I'm also hoping that this epoxy is also going to work as a very good insulator, although I think there should be enough insulation provided by the nylon tube itself. Okay, so we've got that suitably glued up now. So in goes our set of resistors and our brass end. And I think I just want to knock this contact brass tip just slightly inside, so I think a certain amount of violence is called for now. Just want to knock it slightly below the surface so that it isn't proud, so you can't accidentally put your finger on the brass tip. Okay, I'm quite happy with that. Well, no doubt you can see that my workbench is just as untidy as ever, and I thought I'd have a bit of a break from the electronics because I'm still actually faffing around trying to decide on exactly the right circuit to use. So I've just kind of parked the electronics, and I think I'm just going to do some mechanical stuff because that's what I feel like doing. So I've been very, very busy doing some 3D printing, and it's not totally finished yet, but I think I might assemble what I've done so far and make sure that it all goes together. So this is the first part of the ESD gun, which is, of course, we call it an ESD gun, so it has to have a grip and a trigger and a clicky switch. So this is going to be the handle or the gun grip for our ESD gun. So I think what we'll do is we'll go ahead and we'll start to wire this up first. Now, my original idea was to try to put the batteries. I was going to run this from some kind of a 12-volt battery, but to be quite honest, I didn't really think it through very well, or really didn't spend long enough time thinking about it. I wasn't sure what type of batteries to go for, so I have decided to try to run it from an external power supply, and I've got to admit I'm not sure whether that'll be a good idea or not. So I went and bought one of these little I'm not going to call it a wall wart, the kind of thing that powers a laptop. I think it's about 15 volts. So I'll show you that in a bit, but I think we'll just start by having a go at trying to wire up this grip part. Oh, annoyingly, I've just noticed on the back of this switch one of the terminals is a bit bent, so I hope it doesn't break off. I think I'd already gone ahead and tightened this up a little bit, so I think we'll just take that out. I think it might be easier. Okay, let's just figure out what contacts I'm going to use on my Pressy switch, which is those two. So let me just put a mark on there. Use that one and that one. Just recently found these old, I think they call them X-Lite drivers, and they're made from that plastic that smells. They smell like they've been stored for some years up my Wrexham, but I assure you they haven't. Somebody actually gave me these years ago when I first started. It must be nearly 30 years ago, and they were brand new. They give them to me because they were stinking the office out, and 30 years later they still smell just as bad. Okay, so let's solder the wires onto the power connector now. Wow, that's an impressively large solder blob I've managed to get on there, but I'm not going to bother removing it, it can stay. And I actually just kind of designed a groove in the side of the grip. In theory, this power cord, it should fit into there, he said. That's the theory anyway. Okay, that went in. Now I can screw the grip on. Okay, well that seemed to go together okay, but I do seem to have managed to design, purely by accident, perhaps the world's most uncomfortable grip. I really excelled myself. Well done me. So this is the box that I've actually designed to take all the high voltage gubbins, and I've probably made a bit of a design mistake actually, because I've chosen to route the actual power cable to supply the thing through the back of this high voltage box, because the actual electronics box is actually going to sit on top here, and for reasons unknown, again just one of those brain fart moments, I've decided to route the actual power cable through the HV box, potentially exposing it to lots of nasty high voltages. So to be quite honest, I wish I hadn't done that. That was a bit of a mistake. Now of course what I could do is I could just go ahead and either drill a hole in this box or 3D print another one. It wouldn't be the end of the world, would it? But to be quite honest, I can't be bothered. I'm going to give it a try. If it doesn't work, it doesn't work. I'm just a bit concerned that, you know, some of the high voltage arcing, the spark, it might actually couple into this cable and make the control circuit behave badly. Well, as you can see, I've gone ahead and I've just attached our handle to the high voltage box, and you maybe can see that the actual high voltage capacitor here, it's very close to this fixing, the nut, the fixing nut that holds the handle on. And you probably think that that's quite dangerous, and I would actually agree with you, even though that this is the ground side, the 0 volt side. I've actually got a steel nut on here and a steel bolt, but I actually designed this to use a nylon fastener, a nylon bolt. In fact, 3 nylon bolts, one goes there, there and there. But unfortunately, having ordered them, they've not actually arrived. So as you can probably see, our gap is less than 10 millimeters. So if we did have some high voltage on here, it wouldn't have any problems whatsoever jumping onto the head of this bolt, and then it'd probably jump off the head of the bolt onto my finger, which would no doubt be very amusing, but yeah, quite painful. So we need to sort that out, don't we? So the next part that I'm going to assemble, I'm actually calling these the hot ends. So we've basically got this this probe here with the resistors built into it, and I've gone ahead and I've epoxied this into this little mounting boss, and we're going to fix one of the high voltage wires to the back of here, and that's going to feed our high voltage out. But you can see I've got this additional little box here. Well, something quite interesting is going to go in this box. So I've actually designed this little box to fit in it this high voltage relay. So this relay is made by the Pickering company, and I think they're a UK based company. Now these high voltage relays are somewhat specialist. There's not a lot of them around, and I was only actually able to purchase this one via eBay, and this is probably the most expensive part of the project, because I think it was about 30 or 40 pounds, this relay. Now it's not an ideal relay for the job. A lot of these high voltage guns, they use quite substantial vacuum relays that have mercury wetting contacts, and I wasn't able to source one of them even second hand on eBay for, well, I couldn't really find anything under a couple of £100, and to be quite honest, I didn't really want to invest that much money. So this relay is actually only rated for about 7 kilovolt. Well, I'm hoping to actually use it to switch up to about 8 kilovolts. Now, the other thing that the manufacturers warn you against is they do warn you against using it to switch capacitive loads, which is also what I'm going to be doing. So it's quite likely that the life of this relay is going to be quite short-lived. But the reality is, I'm just going to have to suck it and see, because I really didn't want to spend a couple of £100 on a vacuum relay. And I think this is the sort of thing that I'm going to use like once in a blue moon. So, you know, if the relay lasts to do a particular job I need to do, and then I've got to replace it, or maybe I'll just make a bigger box here and I can install one of the vacuum relays if I manage to get one cheap on eBay at some point. Maybe that's what we'll do. But this is what I've got for now. This is what I'm going to use. So I've just been doing some testing with it, so I'm just going to cut them wires off to get it out of the way. And I've got to admit, the way I've designed to mount this, it's quite crude. Effectively, it's just going to stuff in the box like that, and we're going to screw the lid on and forget about him. So we need to put that in. Before I do that, I'm just going to bolt this hot end, this switching enclosure into place. Well, unfortunately, due to my generally poor design, I think there's going to be quite a large amount of swearing going on any moment now, so I think I'll just bring you back when I've finished that. But I've just about managed to get it together, and now we're going to install our high voltage relay. So these orange wires that stick out at either side, they're actually the switched high voltage. The actual coil connections for the relay are here. Unfortunately, this is designed for PCB mounting. Well, I'm not going to do that. I'm just going to solder some wires onto it. So these orange wires are going to be the switch live. So this side is going to go to the capacitor with all the stored charge on it, and the other end is going to go to this, which is going to deliver the spark to our device under test. So this is the thing with the resistors in it. So let's just see if we can get this in here. Now, one thing that I did want to do is I did think that the insulation on this relay looked very, very feeble, so I think we might go ahead and just put a little bit more on. So in theory I can go ahead and screw my hot end on now. I think we'll just put a couple of screws in for now, and I'll come back and put the others in later. Let's just get it assembled. Now the other side of our high voltage relay, it's actually going to fix to one side of this capacitor. So and I'm going to do that via a crimp terminal. That's what I've decided to do. So I need to just put some insulation on here. Now the other connection that I've got to make on our ESD gun is actually the ground connection, because we need to ground the piece of equipment that we're testing. So I think what I've got is this is the inside of a piece of coaxial cable. So this is quite a thick braid, and the reason that I've decided to use this thick braid is you want something that's very low inductance. We want to really have a really sharp rise time. So again, this is quite a long piece of cable, so you don't want to use a long thin piece of cable which would be quite inductive. You want to use a fat wide braid if possible, so that's what I'm going to use here. So I think we're going to have to go for something like that. Well, as you can see, I've gone ahead and I've done a lot of the mechanical assembly now of our ESD gun. So you can see that I've installed the high voltage doorknob capacitor here. So that's the thing that's going to hold the charge, and we're going to discharge that into our device under test, and that's using this high voltage relay. And then we've got the resistors inside here which are representing our human finger. You can also see this thing here, this red tube. Well, you probably guessed it is actually just a resistor, but it is rather a special resistor in that it's I think this one's designed for about 10 or 15,000 volts. And again, a lot of these high voltage components, they're just not available off the shelf. So this I had to buy from eBay. You can't buy them from, you know, Rapid or Farnell or RS and, you know, the usual suppliers. It's just too specialist, and it was actually quite expensive. I mean, how many of you have paid like I think it was about £8 for a single resistor? Wow, that kind of breaks my bank anyway, so that was quite expensive. And that's on top of this capacitor here, which again, I think the capacitor was about 20 or 30 pounds as well. It was relatively expensive. These high voltage capacitors here, the two that I'm using, they as just a smoothing. Now they again, I think they're probably a couple of pounds each, as is this one, which is being used as the Vardy doubler circuit. And again, the high voltage diodes, which are rated, I think these are actually rated for about 15,000 volts. So all this is kind of quite specialist. It's not necessarily available off the shelf, so it does make it that little bit more expensive. And I've also gone ahead and I've tried to just move these wires as far away as possible from the high voltage transformer here, but what I think I will do is I'm going to make a shroud that will clip over this and give us a little bit more isolation. As I say, it was a bit of a design mistake running this cable through the box here. What I should have done is I should have drilled a hole in the bottom there, and I should have just taken it from the connector via the switch. I should have just brought it into the control box here. But yeah, that was my mistake. Now the other thing that we've got to change out before we run it, remember, I've got to change these metal bolts here. I've got to put some nylon screws in. So again, they haven't arrived yet, so they're still on order. I've also gone ahead and I've screwed on the control box, so that's going to sit up here like this, and it's going to have a couple of modes. That one's going to be an on and off switch, and then this switch here, we're going to be able to have the output constantly energized, or we'll be able to select this switch here, and what it'll do is it'll modulate this relay so we can get a pulsed output from the ESD gun. And I'm thinking of making it pulse maybe about once a second, because a lot of these EMC tests, you don't just do like one zap. You like commonly apply 12 or 15 discharges into the piece of equipment under test. So rather than pulling the trigger repeatedly like that, I just thought it's somewhat gilding the lily. We'll put something on it so we can actually just modulate the relay Now I've also just gone ahead and I've just put some sleeving over the earth return cable. It was actually quite a thick braid that I removed from an old piece of coax, and it had some breaks in the braid which, you know, left sharp edges to it. I didn't want to catch my fingers on it, so I've just sleeved it, and I've put some adhesive heatsink at each end and this crocodile clip. So this crocodile clip will probably, I'm not exactly sure, it'd probably go either to the piece of equipment that I'm testing, or we would clip this onto the ground plane. I'm sure it would actually depend on the type of test we're actually doing. Maybe we'll get into that in another instalment. But I think for today, I think once again I'd been beaten off by Grandmaster Time, and can't really go any further. I'll bring you back in part 3 where we're going to have a look at the electronics and the circuit board, because I've actually been developing that behind the scenes, so we'll have a look at that. But I think for today that'll do. So as always, thanks very much for watching, and I hope to see you again very soon. Until then, bye bye for now. Bye.